Right, before we move to the slides, let me just share with you this website. Can you see this website on the screen?
Yes, sir.
Okay, good. Okay, this website is called PV Education, Photovoltaic Education. Even though the main content is tailored or customized for solar cells, photovoltaics generally, if you look at the contents, the outline shown on this website, you can actually a lot of topics that are very related to this course. For example, okay, so you can come to this PV education. You can just go Google search PV education, and then you're going to end up with this pveducation.org. Then you click that website. You can see on this. Let me just scroll down a little bit so that you can see. It starts off with properties of sunlight, which is very much related to solar cells. If you're working on solar cells or interested in solar cells, you can, of course, can use this website to learn more. You can come and see this chapter 3, okay, which is very related to what we're learning now in this course 386. You can see semiconductor materials, something that we have discussed earlier on in the first week of our lecture, and then semiconductor structure, conduction, concept of band gap, intrinsic carrier, doping, which is extrinsic, equilibrium carrier concentration, generation, absorption of light, which are the things that we're going to learn later on in the next topic after carrier transport, right? Generation, recombination, carrier lifetime, diffusion length, all of these topics, if you look at the chapter 3, these are the key topics that we're going to cover in the first part of our course, okay, which is mainly for the physics or the semiconductor materials, right? So up to PN junction, quasi-neutral region, wide base, narrow base diodes and stuff, right? In the second part later on of this course, you're going to cover various devices like transistors, solar cells, LEDs, detectors, lasers, and others, okay, and others. So for those, the contents are going to be different. Okay, this website is mainly for solar cell. So the first part of this course, as I said, can be mainly found from this part, chapter 3. Okay. But if you want to learn a lot more on solar cell, then obviously you can come here and see, learn about solar cell operation, the design of solar cell, manufacturing, the panels, the measurements involved, material properties and batteries, and so on and so forth. So if you are interested, for example, if you want to join any solar companies for your internship later on next year, so the materials that you need to prepare are pretty much here on this website. Okay, your preparation, your readings, and if you want to work in this field as well, obviously you can always come back to this website and learn more. Okay, it's a very comprehensive website for solar cell and manufacturing as well. Okay, so done. Let me just go back to the slide. So if you have anything that you couldn't understand, for example, from this part, you can always come here and look for, you know, animations and explanations from chapter 3 for the topics that we've covered all this while, and the ones that we are going to cover until before the mid-sem break. Okay, now let me just go back to the slides and we'll move on with the calculation. Okay, could you please confirm if you can see the slides on the screen? Okay, thank you. So we have covered last week the variation of EF with doping, And then we've also discussed on the variation of EF with temperature. So we learn about this curve where we discussed about the freeze out region where the temperature is really, really low, starting from T0 Kelvin up to around 100 Kelvin. And then we discussed about the middle region, which is the extrinsic region, where the dopants are 100% ionized, and they play their own their roles in the conduction of the electricity in the semiconductor material. And eventually, we discussed about this high temperature region where you can convert your extrinsic semiconductor to intrinsic semiconductor. Okay, so we've also discussed about two ways that we can adopt in order to reverse the polarity of a semiconductor from extrinsic to intrinsic. So the first one being this one, this curve, where you can just heat up your semiconductor material to produce a lot of intrinsic carriers up to the point when your Ni equals to Nd or Na, if you like, and you can even exceed Nd or Na, and your intrinsic carriers will dominate. And at that point, your semiconductor is going to exhibit intrinsic semiconductor properties. So can you recall the second way that we can do in order to reverse the polarity or to convert your extrinsic to intrinsic? What is the second way to do that? Anyone? Okay, Bala said doping. Can you elaborate a bit, Bala? How do you go about doing doping in order to reverse the polarity or the properties? Can I
Uh,
answer yourself? Yep.
if it's an N-type semiconductor, you dope it with a trivalent dopant. So, for example, boron, I think, something as an example. So it will
Yep.
reverse the excess electrons into holes and counteract, and you might get back an intrinsic semiconductor.
Yeah. Very good. And that is called what? The concept is called what? What semiconductor? The term of that semiconductor material in that case? Starting with C, we discussed last week. The act of reversing the polarity by incorporating the opposite dopants into the lattice in order to reverse or to reduce the majority carriers, and eventually you get your holes equals to electrons in the lattice. What is the concept that we learned? Starting from C, anyone? Compensated, right? Good for that. Compensated semiconductor, right? So you can compensate by incorporating reverse polarity dopants. So if you start off with N-type semiconductor, just like what Bala said, you can incorporate borons, for example, into the lattice in order to compensate the N-type to make it P-type compensated semiconductor. Okay, P-type compensated semiconductor, and the reverse or the opposite is always correct as well. You can start off with P-type and then you incorporate electrons, and you eventually end up with N-type compensated semiconductor. Okay, so let's just go through the first example from the three examples. I'm just gonna let you explore the remaining. So let's discuss this example number one. So look at this example on this page. You can see EC, EV, EF. You can see the EG, which is the distance between EC and EV, is given by EG, right? That's essentially EG, 1.12. And the distance between your EF and EV is 0.8 electron volt. So the question is, the band structure of a silicon, Ni equals to 1 times 10 to the 10 per centimeter cube, is shown here. The sample is at 300 Kelvin. Answer the following questions. Note that the NC is given as what we discussed before when we talk about density of states for electrons in the conduction band, equals to 6.2 times 10 to the 15 times T to the power of 1.5, okay, per centimeter cube. And NV is given as well, 3.5 times 10 to the 15 times T to the power of 1.5 per centimeter cube. The question is, what is the doping type of this semiconductor material? Is it n-type or p-type, and why is it so? Right, anyone? Is it n-type or p-type? And why? I think we've discussed this one briefly last time as well. Let's just recap. N-type, Bala, okay. Why is it n-type, Bala? Haziq, n-type, yep. Okay, why is it n-type? Yes, EF is near EC, okay? Simple. EF is near to EC than to EV, right? The moment you can see your EF is skewed to one direction, either EC or EV, in this case EC, then it's n-type. If you see EV closer to EV, then it's p-type. Very, very easy, right? So that's the reason for the n-type semiconductor properties. So what is then the dopant density? How do you determine dopant density? So it's given already, right? So you can just see from here, the equation is already given. We've discussed last time from density of free electrons, remember, equals to NC exponential of EF minus EC over KT. So your NC is already given, 6.2 times 10 to the 15 times T to the power 1.5. So you just can plug in the value given, 6.2, and the T is known, 300 Kelvin, exponential EF. What is EF now? EF is about 0.8 with reference to EV, remember? And your EC with reference to EV, so that is a 1.12. And your KT is known because your K is a constant and T is known, is given. So then you're going to get 1.4 times 10 to the 14. Okay, 1.4 times 10 to the 14 per centimeter cube. So your N here, is it your majority carrier or your minority carrier? Anyone? Your N in this case is your majority carrier or your minority carrier? Haziq? Semua cakap majority. Bala majority, Najia majority. Haziq, what do you think? Majority or minority?
Major, Doktor, major.
Kenapa majority? Why majority carriers? Any reason? How about others? Why majority carriers? Zohan, majority or minority, and why? Okay, Zohan said majority. Why majority, Zohan? Can you unmute yourself? Kenapa majority? No one said minority. Why is it majority? Anyone wants to answer that? Why N is your majority? Because electron is your dominant carriers, right? And we knew it already from the n-type in the question part A. Okay, n-type, therefore electrons are the majority carriers. Soalan ni simple je. It's not, well, it's very straightforward, but then when you ask why, it becomes a bit tricky as of what is expected as the answer. Okay, you can always relate back to the EF position, right? Because you started off with n-type, and therefore in n-type electron is majority carrier. Simple, eh? So what is then the minority carrier concentration in the sample at thermal equilibrium? How do you determine the minority then? Okay, kita belajar. What is this? What is this equation called? Equation number 3 ini yang kita I'm showing you on the answer. What is this called? To determine the minority carriers once you know the majority carriers. What is this equation called? What is it called? Molar of L. Law of mass action, right? Law of mass action. So whenever you are asked to determine the minority carriers, go back to law of mass action. That's it. Okay, minority carriers use law of mass action, NP squared. N times P equals NS squared. Your N is already known from the previous calculation, right? And then your Ni is already given. 1 times 10 to the 10. Okay, you can just use 10 to the 10, square that, and then you're going to divide your majority with your do you notice anything wrong in this calculation? Anyone notice anything wrong in the calculation? Or not so right, if you like? Ada tak kesilapan dalam calculation ni? Good. Bala. So if you see the question, what is the NI given? 1.0, right? So but the calculation used 1.5. Well, it's my mistake, but then I want you to realize that, right? It's my mistake. If the question doesn't say your NI, you can use either one. But if the question says NI 1 times 10, you can use you should use 1.0 times 10. But if you use 1.5, I am not going to penalize you because it's correct as well. It's just that you don't follow exactly the question, right? So then your Ni squared divide by your majority carriers, you're then going to get your minority carriers, 1.6 times 10 to the 10. Okay. So I'm going to leave you with the example number 2 and number 3 for you to try out. So let's move on to the next topic, which is carrier transport phenomena. We're supposed to start that this week. So let me just share with you the slides on the carrier transport. So up to this point, it's not that complicated yet, okay? Because we're still learning about what's happening in each material in one semiconductor material, okay? It is still relatively easy for you to understand. So the moment it's going to get more and more complicated the moment we combine two materials, right? As a junction, P and N, N or P. In some cases, you can input intrinsic in the middle as NIP, or it can be PIN, right? It's going to get more and more complicated that in terms of the physics concept and in terms of the calculations as well, right? So the next topic that we're going to cover is called carrier transport phenomena, okay? So we're going to look at how do the carriers move in a semiconductor materials, right? And these type of movement or motion are going to take place in the semiconductor devices as well, eventually, right? So let's just recap on challenge what you've learned from the previous topic before we move on so that everyone is on the same page. So let's go to question number 1. Define intrinsic semiconductor. What is an intrinsic semiconductor? Anyone? Let's just recap for a while. Undoped, right? Okay, good. Intrinsic means undoped or pure semiconductor. There is no dopants incorporated into the lattice. Simple. Okay, that is intrinsic. Right, the second one. What is the source of electrons and holes in intrinsic semiconductors? What is the source of electrons and holes in intrinsic semiconductors? Where do you get your carriers in intrinsic semiconductors? Or rather, how do you get your carriers in intrinsic semiconductors? Anyone? Thermal excitation. All right, good. Thermal excitation. How do you get? What triggers thermal excitation, Bala? What makes you get thermal excitation? You get your carriers from thermal excitation, correct? What induces thermal excitation? Anyone? Apa yang induce thermal excitation? Ravin, can you unmute yourself? Tak dengar Ravin pula. Tak dengar Ravin lagi ni. Ravin, any idea? Where do you get thermal excitation, Ravin? Yes, Ravin. I can see you unmute, but I couldn't hear you. Can you unmute yourself? Yeah, I can see it's unmuted already, but I couldn't hear you. I'm not sure why. Try cakap, Ravin? Or are you talking now, but I'm not listening? I don't hear you. Okay, write down as well, Ravin. When the heat supply is greater than Eg, okay? Good. When the heat, your mic's not working, that's fine, right? It's okay. So you are supplying the heat to the semiconductor, okay? So temperature increase or exactly heat to be exact. Equal to Eg, okay? Good. So thermal excitation is caused by the heat or the temperature increase, leading to thermal excitation of electrons and hole in intrinsic semiconductor. Good. Sekarang dah tahu intrinsic punya carrier dapat dari mana. Next, define extrinsic semiconductor. Anyone? Senang je kan? Dope, right? Tadi undope, sekarang dope lah. Right? You're incorporating dopants into the lattice. Can be p-type, can be n-type. Trivalent for P, pentavalent for N. Okay, clear. Very simple. You are given a p-type. Kita dah discuss soal ni. How you are given a p-type silicon wafer, how do you turn it into intrinsic? Okay, tadi Bala dah jawab tadi. So the first one is compensated semiconductor. The concept is called compensated. You can just reverse the polarity of the majority carriers. Holes in this case can incorporate more and more phosphorus in the lattice to compensate the semiconductor. And then the second one, what was it? Kita baru discuss tadi. How do you turn this to be intrinsic? What was the second one that we can do in order to turn this p-type into intrinsic again? Baru discuss tadi last 5 minutes. Heat it up, right? Heat it up until it becomes intrinsic. So if you're given this question, for example, make sure you can sketch or you can draw this diagram, right? And label this accordingly, X, Y, whatever. Also, you need bukan Y. I don't mean the axis. I mean parameter A and B. Okay, don't get me wrong. So freeze out extrinsic in the middle and then intrinsic here. And the moment your Ni equals to Nd or Ni equals to Na, right? Depending on whether you're talking about p-type or n-type. Okay, you should be able to draw that and explain all the three regions. Okay, heat up, heat up. Okay, so when you're given questions like this, for example, katalah you ada satu soalan, you don't just answer, you compensate and you just heat up. That's it. Right? So what I've seen from previous batches of students, sometimes I see students who cannot gauge the level of details expected from questions. For example, the question is asking you a certain explanation and it gives you 20 marks, for example. 20 marks, contoh. So this question could carry 20 marks, for example. Ada student yang bila jawab, just jawab dua bullet point je. Satu compensated, satu heat up. That's it. And then expecting 20 marks. Of course, you won't get 20 marks. You should be able to elaborate. You should be able to draw. Okay. You should be able to gauge what is expected from the questions. Okay. Kalau dia cakap, let's say 2 mark, then it's probably just listing 1 and 2. If it's given, if it's 20 mark, if 20 mark is given, then obviously you should expect some elaboration, some sketches perhaps. Okay, should be able to gauge that. So that's one of the skills that you should develop as well. Okay. So in this topic, we're gonna look at introduction to carrier transport or charge transport. Same thing. When I talk about carrier transport, so I'm also talking about charge transport. Same thing. Carriers are charges. Okay, carriers are charges. Then we're gonna look at drift. The concept of drift. What is drift? Kalau kereta tu yang drift kereta, this one is drift of your carriers in the semiconductor material. And the second one is called diffusion. Okay, diffusion concept. And then the last thing that we're going to cover is called Hall effect. Anyone working on Hall effect for your FYP? Ada ke? Anyone doing Hall effect for your FYP? Mesti ada kan? Anyone working on doping or polarity or measurement of your resistance or something? I think some of you might be working on Hall effect as well. Right, charge transport is the movement of charge carriers around semiconductor or within semiconductor. Okay, how do they move about in the semiconductor? So the first type of charge transport is called drift. Okay, so drift is movement of electrical charges or carriers. Either one is fine, due to presence of electric field. Okay, movement of electrical charges or carriers due to presence of electric field. That means to be able to have a drift component, you need to have electric field in the first place in the system or applied to the semiconductor. Then only you can expect drift component to be there. If there is no electric field, there will not be any drift component at all, right? The second type of charge transport is called diffusion. Okay, diffusion. Diffusion is movement of electrical charges or carriers due to presence of concentration gradient. Okay, concentration gradient. That means for diffusion to take place, the carriers should be able to first see a gradient of concentration between one spot versus another spot, or one region versus another region, one side versus another side. So there should be a difference of concentration gradient. So that means if you're talking about side A and B, there shouldn't be similarity in terms of the level of concentration between side A and B in terms of the concentration of carriers. If you don't get any difference in terms of the concentration gradient, then you shouldn't expect any diffusion to take place. Okay, so let's have a look at the details of the charge transport before we move on to drift and diffusion. We'll also cover a concept that's called thermal velocity in charge transport. Consider free charge carriers moving in a semiconductor due to thermal energy from the lattice. Discussing about semiconductor material being placed at different temperatures. It may range from 0 Kelvin up to say 100 Kelvin, 200, 300 with increasing temperature if you like, right? And this increased temperature carries along thermal energy within the system, and this affects the movement of the charge carriers as well. All free charge carriers move with an average velocity called thermal velocity. Okay, this is a concept that's called thermal velocity. At room temperature, the thermal velocity is somewhere around 10 to the 7 centimeter per second. Okay, 10 to the 7, and that is equal to 360 kilometer per hour. Very, very high. Free charge carriers are scattered by the host lattice, by dopant atoms, by other impurities as well. So the moment you have your charge carriers moving within the lattice, there will be possibilities where they're going to get scattered. Akan ada collision, akan ada pelanggaran, and hence scattering. Dia akan ada pelanggaran, and then you're going to change direction because of some scattering by the host lattice itself, by the host lattice of silicon, for example, by dopant atoms present in the lattice due to doping process. Kalau you ada extrinsic semiconductor, then you're talking about charge carriers movement. They are going to experience scattering by the host lattice from the silicon, by the dopant atom as well. So the carriers are going to be scattered by the presence of phosphorus, by the presence of boron, by the presence of arsenic, antimony, depending on what you have in the lattice, and by other impurities as well. So you may have impurities in the lattice that are not intended. Remember last time we talked about intended impurities and unintended impurities. So if you have, say, defects like copper or nickel, platinum that are unwanted in the lattice in the first place, they are present in the lattice and they affect the movement of carriers as well. And they present themselves as defects. They're going to learn later on when we talk about recombination. Okay. If there is no electric field and there's no concentration gradient, okay, remember these two keywords. If there's no electric field and there is no concentration gradient, the direction of the thermal velocity after each scattering is random. Okay. If there is no electric field present, hence there is no what component. If there's no electric field, then there's no what component that we discussed in the previous page. Anyone? There's no drift. Good. And if there is no concentration gradient, hence there is no what component? Got that, the concentration gradient? What's the second one? What's the second charge transport? Yep, diffusion. So there's no electric field, there's no concentration gradient, hence we are not expecting any drift. Hence we're not expecting any diffusion. Hence, or therefore, the direction of thermal velocity or the direction of the carriers in this case is random. Okay, they're the random motion. There will be like this. There'll be just scattering happening with the lattice, with the dopants, and there's no net direction of the movement, if you like. Okay, there's no net direction of the movement. There's no specific direction. They can just be random, and you couldn't tell any specific direction. And the net is even zero, right? Thus, the net velocity of all the free carriers combined is zero, right? There's no net movement, no net transfer of charge. You don't get the carriers to gradually move into the right direction or into the left direction or into the upper direction, the lower direction. No, there's no net movement because they will just be random overall. The path of the carrier is characterized by a mean free time between subsequent scattering events, right? The path of the carrier is characterized by mean free time between subsequent scattering events. So that means between the current scatterings, pelanggaran yang berlaku sekarang, katalah dia langgar sekarang dengan lattice, boom, done, till the next collision. So that is called mean free time. Okay. Kalau you ada longer mean free time, that means the frequency of collision will not be as high because there'll be time, a long time before they experience the next collision or the next scattering. So that means your mean free time in that case is quite long. On the other hand, if they experience very frequent scattering or very frequent collision with the lattice or dopants or whatever, other impurities, so that means the mean free time will be very, very short because now you get your scattering done, you just experience scattering, and then before they realize they are already scattered by the next scattering event, right? We call that scattering event, the collision. Okay, so this is how they are characterized when you talk about there's no electric field and there's no concentration gradient present. Okay, so now let's have a look at drift. Okay, drift, the link is on the PVC ROM. Let's have a look later on. I'm going to share with you the website eventually. Drift is the movement of electrical charges or the carriers due to the presence of electric field, as discussed. A free electron moving in an electric field E has a net velocity in a direction opposite to the electric field. So electron moving in an electric field has a net velocity in a direction opposite to the direction of electric field. So if the electric field is pointing to the right, then electron is moving to the left, and vice versa for holes. So let's just go back to the website, and we're going to see some simple animation to demonstrate this. Yeah, let me unshare these and go back to the website on Rift. Okay. Mana website tadi? Let me just click on the website first. Okay, hold on. Share, go back to the website. All right, can you see the website on the screen?
Yes, sir.
Right, good. So let's go for drift. Mana drift. Yeah, drift is here, chapter 3, right in the middle. Okay, just click drift. Okay, now you are seeing the drift page, right? Just to confirm, just in case. Nampak drift?
Yes, sir.
Cool. Right, so drift carrier transport when electric field is imposed on semiconductor or electric field is present. Electrons move in the net direction opposite to the electric field. Holes move in the direction of electric field. So holes follow the direction of electric field and electrons going opposite to the direction of electric field. So let's have a look at the effect of drift. Okay, just come down here to the animation. Okay, let's play a few. So the animation shows how the presence of electric field will introduce a net distance to the movement of carrier. In this animation, the carrier is whole so that the movement is in the direction of electric field. So let's just start and see. So there's no electric field. If you don't see the animation, let me know. I think you can see that. So you can see there's no electric field applied and the direction is completely random. Okay, there's no direction. Yang tadi untuk atas, huh? So now let's see the second portion here, the below portion, where you have electric field imposed to the system, right? Or to the semiconductor. So you can compare with the one without electric field. So even though you can still see some scattering, for example, in various directions for the case of with electric field, there is still a net motion in one direction, okay? So let's just restart and see this. Start tengok atas dulu, no electric field. So it's completely random, there's no net movement. So if you do the net, it will just be 0, right? So on the other hand, if you go to with electric field, you can see it's being scattered into random direction, but there is still a net motion of the carriers, right? So they're still scattered, but then you see it's moving into one direction, and it's going to the left as well sometimes, but most of the times it's going to the right, and therefore the net is to the right. Okay, the net is to the right. So what happens here in the second animation, so the animation above shows randomly carriers with and without electric field. The application of electric field causes a net movement of an electron in this case, towards the right and hole to the left. Okay, sekarang kita nak tengok electron and hole. Electron is the red one, red particle. Hole is the blue particle. So let's see. Start. Tengok ada kat atas electric field. Macam it's just movement is only about a position, right? There's no net motion. But then you can see for the case of electric field, with electric field, you can see it's still moving about pretty much the same location, but then it's moving into one specific direction. Right? So tengok sekali lagi for the second case. So let's just restart. Look at the blue particle, holes, is going to the left, which is the direction of electric field, and electrons, the red particle, going to the right, opposite of the electric field. Okay. So still moving about, but eventually the net is into one specific direction. Okay. So that's the whole point. Okay. Let's see the third animation. Without electric field, the electrons and hole move about randomly. Now, sekarang electric field is off. Turn the electric field on and watch the electrons and hole drift. Sekarang nampak dia random. So let's just plug on electric field. Sekarang kita nampak electrons are moving into, electrons going to the right or to the left. You can see now. Nampak eventually are they going to the left or to the right, electrons? Can you see the net movement here? Left? Betul ke, Zuki? How about others? Look at the red particle, left. To the left. It's moving to the left, isn't it? So dekat sini pada indicator. You can see electric field pointing to the right, and therefore electrons should be going to the left. And you can see they are moving to the left. Nampak lah, you nampak confused sikit sebab belah kanan tu macam elektron masuk kan. But they are actually travelling to the left. Net movement travelling to the left. And you can see holes on the other hand, they're moving to the right. You can see the very same particle follow dia tengok di kanan. So that's pretty much what's going to happen if you apply electric field to a semiconductor, electrons and holes in the system. Okay. Eventually, we're going to bring the very same concept to the combination of P and N. We combine both as a semiconductor junction, PN junction. We're going to experience the very same thing, except you are combining two different materials now. Okay. And we are very interested to see what happens, particularly at a junction, at the interface between P and N eventually. Perhaps week 6, I think, right? Week 6. Okay. So let's just stop here. So can you see can you understand now the concept of random motion with drift, with and without electric field? Is it clear from these animations? Okay. You can always come back to this website and play for yourself. It's very, very useful. Okay, let me just stop sharing here, go back to the slides and continue. Oh, 10:44 already, so fast. So let's finish in about 5 to 8 minutes, perhaps. Okay, could you please confirm again if you can see a slide, just in case?
Yes, doctor.
Cool, thanks. Right, so let's move on to the next. So this is showing the random motion. Okay, it's governed by F equals to ma and m times dv dt. You can see later on the average collision, the scattering events and stuff. Okay, just elaboration of the very same thing. So let's gonna see. We're gonna see next the concept of drift, and then how does it affect the mobility, and then how does it affect the current associated with drift. Okay. Now consider the density of drifting charge. So since the charge is drifting under the influence of electric field, so the charge is then the carrier. Okay. Given as the density of charge, carriers times the charge per carrier, negative q or plus q. Consider electrons. Okay. If you consider a carrier is an electron, for example, there will be current density associated with the movement of carriers under drift condition. Okay, so we're going to learn later on that when your carriers are experiencing either drift or diffusion, there will be current density associated with the drift or diffusion of holes or electrons. Okay, so for the case of drift of an electron, there will be current density associated with the drift of that electron. So if the same thing goes to, if you're talking about drift for a hole, then there'll be current density associated with drift for that hole. Okay, and eventually you're going to discover that when you talk about diffusion next, there'll be a diffusion current density related to the hole, diffusion current density related to electron as well. Okay, and the current density is given by J. Given by J, and J is equal to Q times N times mu E. Okay, Q times N times mu E. The Q is the electronic charge for electron, and here is the carrier concentration. N is the concentration. So this is how it could be related to your previous topic. Yeah, the calculation of N, the majority that we've learned in the previous calculation. And then the mu here, mu E is the mobility of your electron. Okay, mobility of electron at a particular condition, at a particular condition. So we're going to relate this with various other parameters, temperature, doping level, and whatnot, right? And E here is the electric field applied. Okay, because it is drift component, remember? It is drift component, therefore the E has to be there in the equation. So J then is equal to Q N mu E E. Okay, so if you convert this, if you simplify this, you can also say that your J is equal to your conductivity times E, where your conductivity is equal to these three components. Sama, you just ambil These three only, Q and mu. Q and mu equals to your conductivity. Okay. So Q is the electronic charge, mu mobility, N is the carrier concentration, and you're gonna get your J equals to conductivity times E. Or you can also rearrange your mu to be equals to this equation, right? So let's see how does the mobility come into the picture. So let's finish off with this slide on mobility. So what is mobility of carriers? Mobility of carriers is dependent on the semiconductor itself, the doping density, the temperature, among other things, and it can be measured. Mobility in simple terms is how easy your carriers move in your semiconductor. Okay, if the ease of movement is high, then you're gonna get high mobility. If it's not that easy to move across, then you're gonna get low mobility of your either or electron or hole. Okay, and it can be dependent on many parameters. For example, if you look at this particular graph, you can see your mobility of electron or hole on the y-axis. Okay, so you're gonna see every now and then your mu will be using mu n or mu e. It's referring to the same thing. N here is referring to electron, and E here is referring to electron as well. So in this case, you can see it's using mu n, which is reflecting mu e actually, or it's showing mu p as well. Mu p is actually mu h. Okay, so you boleh guna either mu either one lah. Either one is fine. Either one is fine. So if you want to use either one, N with P or E with H in pair, you can use either one as long as you're consistent and you don't confuse yourself. Kalau nak pakai E and H, then E and H throughout. You nak pakai N and P throughout. Okay, either one is fine. Jangan pakai first calculation pakai mu, second mu E. You confuse, nanti I pun boleh confuse, right? So try to be consistent if you want to use either one. Just use the very same pair. So in this case, it's showing mu n and mu p for the mobility on the y-axis. And this curve is showing you the dependency on the doping level. Okay, the mobility is dependent on the doping level of your semiconductor. For example, let's have a look at silicon. Okay, let's have a look at silicon. The graph is for silicon. And then let's have a look at what is the mobility of your electrons at 1 times 10 to the 16. What's the value of mobility of your electron at the doping level of 1 times 10 to the 16? What do you get? Mobility of electrons at 1 times 10 to the 16. Berapa value dia? What do you see from the graph? 450 electrons, okay? Are you looking at electrons or holes? Electrons. The upper curve, right? The upper curve is for electrons. The lower curve is for holes, right? So what is the value of mobility for your electron at the doping level of 1 times 10 to the 16? Okay, 2500, right? Anything else? Any other answers? Anyone else? Sorry, bukan silap tengok silap tengok scale. So what is it then? Go to 1 times 10 to the 16. Okay, 1248 is already given, right? Isn't it, Bala and Zuki? Saya saja je tanya. Make sure you look at the graph, right? 1 times to the 16 is already given, in fact. Electron 1248, which is there, right? 1 times to the 16 here. You can just check here, but it's going to be 1248, right? And at the same doping level, the mobility of your holes in your semiconductor, in your silicon, is at 437. It's already given there. 1 times 10 to the 16. Okay. So what happens, say, for your electron, what happens to electron mobility if you dope your silicon at 1 times 10 to the 18? what happens to the mobility of your silicon, of your electron in your silicon when you dope it with 10 times 10 to the 18? Decreases, yes. What is the value of the mobility at 1 times 10 to the 18? Anyone? Ini baca graph ya, it's not complicated, it's not rocket science. Just baca graph ya. Electron first. Let's finish with this. Electron first, then hold, then we're going to finish the class. What's the value of electron mobility at 1 times 10 to the 18? About 500. Any other answers? There, 100, 200. Betul ke, Suki? 280. 118 is here, right? Nope, sorry, silap. Tekan pula. 1 times 18 is there. Electrons is there, isn't it? Holes down here. So that's 100. That's 200. That's 300. Before 300, right? So under 300. Yeah, 10 to 80 or so, right? For electrons is 280. So now let's see the difference. So now you start off 280. Tadi kita dapat 1248 centimeter squared per volt second, isn't it? At 1016. And then when you increase the doping level to 1018, 2 orders of magnitude higher than the previous case, now the mobility reduces tremendously to 280. Okay, about 5 times, pretty much 4 or 5 times lower than the previous one. Why do you think it's reducing? Why do you think it's reducing? Apa, when you dope at high doping level at 1018 with reference to 1016, your mobility of electron reduces by about 4 times. You can calculate to be exact. It's about 4 times, more or less. Huh? Okay, you're saying because more collisions between electrons. Are you saying collision between electrons to electrons? Okay. Or any other answers? Any other opinions? Why do you think when you dope your silicon at doping level, in this case 10 to the 18, your mobility is reduced by about 4 times? Pretty much. Any other answers? Any other opinion? We're going to cover this eventually in the next few pages, but let's just get your opinion first. What do you think? Electrons scattered instead of moving in one direction. Yes, it is scattered, but scattered due to what? Why do you think, what is the reason for the scattering? Or at least, what is it scattered with? 1248 bahagi 280. Let's say 280. So that's about 4.45 times lower. 4.5 times lower. Yeah, Zohan. Collision between electrons and impurities. And where is the origin of the impurities? Why impurities are there? Zohan, why do you think impurities are there? Why increase collision between electrons and impurities? Kenapa dia lagi banyak langgar? Exactly, right? Because of the doping. Doping are impurities. Okay, you incorporate more and more dopant atoms into the lattice. If you like, macam you are in one office room or one or your master bedroom lah, for example, and then you are just alone in the room. So you are the electron. You get to move freely, isn't it? And then suddenly your friends coming in for a birthday party or whatever, and in the very same room you have now 30 people coming for your birthday party, and it's getting crowded now. So beforehand, before your birthday party started, you can move easily to the kitchen, to the toilet. You can walk, easily. Tutup mata pun sampai lah. But then when you have your birthday party started, you really have to, go through people so that you tak langgar dengan orang lain lah. So that's pretty much the analogy. Okay, because now the moment you increase doping level from 1016 to 1018, there are more and more impurities incorporated into the lattice. And if you like, the lattice gets more busier and crowded, and hence more collisions, right? The moment you have more collisions, remember, go back to the definition of the mobility, the ease of movement, right? Senang tak the carriers move within the lattice to do the conduction and so on and so forth. It's now a lot harder to do because you have impurities in between. So when they are trying to move within the lattice, they get to experience more and more collisions, right? Due to the presence of impurities in the lattice. So that's the very there's a very reason why do we see 4.5 times reduction in the electron mobility when you increase doping level from 10 to the 16 and 10 to the 18. And the very same thing is experienced by the hole as well. So except the magnitude is a bit different, you can work out for yourself. 437 at 1016, and that's about what 100 plus, 150 perhaps, or 170 for the doping level of 1018, the mobility, right? So the reduction is not that steep if you compare to the electrons, but the very same reason still persists, right? They get to experience more and more collisions if you increase doping level to a higher level. Okay, so that's very essence of the gist of this mobility dependence on doping. So is it okay so far? I'm just going to stop here. We're going to discuss a lot more on the impurity scattering and the lattice scattering as well, which is also dependent on the temperature in the next slides onwards. Any questions so far on carrier transport? Can everyone follow? Okay, semua paham, eh? Good. If there's no question, then I'll see you again tomorrow, 4 p.m., right? 4 p.m. Okay, bye-bye. Take care. Assalamualaikum. So my FYP students can just stay because we have a meeting now at 11. Zik, Zul, Najihah, Fatul.